Okay. Hi everyone, my name is Shivansh and we are going to learn about a new topic called magnetism. Magnets are objects that you are very familiar with. In your previous classes, you've seen and you might have actually done experiments in your labs, or you might actually have toys that use magnets. When you were in class 10th, you studied about electric motors and DC and AC generators, which actually used magnets to generate electricity. You remember that we used to have a horseshoe magnet, and inside of that horseshoe magnet we used to put a coil, and then that coil would actually rotate and then generate electricity. Yeah, so that is a magnet, right? And let's do a quick recap of what we have studied about magnets in our previous classes. And for that purpose, we're going to assume that this marker is a magnet. However, you would know that this marker is made of plastic, and plastics cannot be magnetized. This actually cannot be a magnet. I'm just assuming that this is a magnet. There are magnetic materials that can be magnetized, but this is not one of them. Let's assume that this is a magnet, and this is the north pole and this is the south pole of this magnet. And there's another marker, this is also a magnet. This is the north pole and this is the south pole of this marker. What I'm going to do is that I'm going to tell you that when I take the north pole of this magnet and the north pole of this magnet and I put them together, they actually tend to repel each other. When they come close to each other, they repel each other. And you must have actually noticed this in your toys. There are playing magnets that you can actually buy from the market, and then you can do this little experiment and you will see that like poles repel each other. And obviously I don't think I have to explain that if north pole and north pole are actually repelling each other, also the south pole and the south pole will also repel each other. I mean, that's kind of obvious, right? So let's try to understand this. Let's make a quick diagram to understand this. We'll make a magnet like this. Here I'm going to mark the south pole, here I'm going to mark the north pole, and another magnet whose north pole is close to this north pole. Alright, so because of this arrangement, what will happen is that they will start repelling each other, right? And the same story goes on if I take a south pole over here and a south pole over here, and then again I will see that a certain repulsion will happen. Okay, so these are all repelling forces. And conversely, that is true that if I take the south pole of this magnet, which is this one, and the north pole of this magnet, and when I bring them closer, they will just attach with each other, right? And it's kind of fun when you do it with toys. I wish I had those toys, but for now we have to make do with these markers, which are not magnets, and we have to imagine that they are magnets. So if I make a north pole over here and a south pole over here, and for another magnet, if I make a north pole over here, now see I'm attaching unlike poles closer to each other. So what I'm going to see is this magnet actually experiences a force on this side, yeah, and this magnet actually experiences a force on this side. So I can confidently say that unlike poles, and what are unlike poles over here? Unlike poles are north and south. What would be like poles? Like poles would be north-north or south-south. So unlike poles attract each other. And this force is actually attractive force. And this is pretty much what we have seen in our previous classes. So we don't really know why this happens, right? That's the problem. We know that this happens, but we don't know why this happens. And this is pretty much the people in history were actually concerned with that. They found magnets in natural habitats. They found rocks that contained magnetic materials, and they were behaving in a certain way, and they did not know how they actually work, right? So in this chapter, we are trying to understand how they actually work. So remember we studied waves in our last class as in class 11th. When we were studying waves, we studied about something called mechanical waves and also electromagnetic waves, right? So over there we had a discussion that light is an electromagnetic wave, right? And if light travels in this direction, let's assume that light is traveling in this direction, then it will actually have fluctuations of electric and magnetic field, right? And the fluctuation of electric field would look like this, and the fluctuation of magnetic field would look like this. So I believe that was the first time when you were first introduced to something called magnetic field. You already know what electric field is. I mean, you have studied all these chapters on electric field, electric charges, electric potential, capacitance, and what's that? Gauss law. You studied all of that, and after passing all of that, after completing all of that, we have come to this chapter. You already are familiar with that electric field. It is denoted with a capital E and a vector sign on top. However, magnetic field is denoted with a capital B and a vector sign on top, because obviously magnetic field is also a vector. So yeah, magnetic field is also a vector quantity. Just like how electric field is a vector quantity, magnetic field is also a vector quantity. So do you see some pattern over here? And the pattern over here is that if there is a fluctuation in electric field, there is also a fluctuation in magnetic field, which means electric field and magnetic field can be understood as two sides of the same field, which is actually called the electromagnetic field, right? We have already covered what electric field is, and it's time to begin understanding what magnetic field is, right? And I would also like to draw your attention towards something that you studied in the chapter of electric field, which was Coulomb's law. I'm pretty sure you will be able to recall what Coulomb's law was. Coulomb's law told you that electric field varies as an inverse square of the distance, and it is directly proportional to the strength of charge in coulombs, right? And in order to find the direction of it, we would put an r cap over here, where this r cap would be a unit vector in the direction of the radial distance, right? And k was the universal constant, Coulombic constant was 9 into 10 to the power 9, and the units were Newton meter square upon Coulomb square, right? And if you remember that we also used to write it as 1 upon 4 pi epsilon naught. You already know all of these things, where epsilon naught is the permittivity of free space, right? And I told you that electric and magnetic field are very similar to each other, and yet very different from each other. What you see in magnetic field, what similarity you see in magnetic field over here is that there is a law in magnetic field called Biot-Savart law. And it looks very similar to the Coulomb's law, and we will study how it works. What that law actually looks like is that magnetic field, or I should rather say dB, and by dB what I mean is small magnetic field. dB becomes equal to, sorry about that, dB is equals to mu naught divided by 4 pi. This is mu naught divided by 4 pi times I dl cross r cap over r square. Okay, now at the first glance you may be thinking that this looks nothing like the Coulomb's law, but if I'll explain it to you, you will actually start seeing that. So you see that there is a mu naught upon 4 pi over here. This is very similar to the k over here, alright? K used to be 1 upon 4 pi epsilon naught. So there is a 1 upon 4 pi for both. Instead of an epsilon naught in the denominator, we have a mu naught in the numerator, right? And we have a similar inverse square relationship for the for distance. So magnetic field also decreases as radius, or I should say the distance increases. And this is actually current. This is current. And this is dl. dl is a small length along the current. And this is cross r cap, and this is again the radius vector. So what was the most important thing about electric field? Electric field originated from charge as given by this formula, right? You see something similar going on over here? Yes, something similar over here is current. Current. Now current is the one that actually generates magnetic field. And that is super mind-blowing. You know why? I'll tell you why. Let me clear this board first. It's super fascinating because there was this scientist called Oersted who knew that magnetism and magnetic field has got something to do with charges, right? So what he did was, he took a wire. Right? And there was current flowing through this wire. And he put a charge over here, a charge body over here. Do you expect this charge to feel some force? Obviously not, because in electric current we have studied that as much current flows through the wire, it does not make the wire electrically charged, because equal amount of charge comes in and equal amount of charge goes out, which means the wire is neutral. So how can a neutral thing force a charge? It can't, right? And well, it didn't, of course, because there is no force, there is no electrostatic force between the wire and the charge. But the moment when this charge moved, the moment when this charge was given a velocity, what Oersted saw, what Oersted actually observed in his experiment was that this moving charge actually turned. Like me. So the strange thing over here is that two things that should not force each other are forcing each other. And this new kind of force is definitely not electrostatic in nature. It is some new kind of force. And this force was turned magnetic force because Oersted also brought a magnetic compass near it. And he saw that the electric current flowing through this wire when it was switched on was actually deflecting this magnet inside the compass, just like it was deflecting the charge which started moving. Which means that when charges start moving, which we also know as electric current, when charges move it becomes electric current, right? When charges start moving, they start forcing each other in a way which is not electrostatic in nature. However, it is similar to magnets, how magnets force and attract each other or repel each other. That was why it was hence concluded that moving charges are responsible for producing magnetism, which was then later proved by Biot-Savart in his law, which I just wrote down a while ago, that magnetic field is given by mu naught upon 4 pi multiplied by I dl cross r upon r cube, and some people also like to write it as I dl cross r cap upon r square. And this formula actually looks very similar to the Coulomb's law. Okay, so this is where the entire story of magnetism generated. And what we do in this chapter is, we just saw two really important things happening. We saw that a current was producing something which forced a moving charge, and that something is called a magnetic field. We will come to that later. So current produces field, that's one part of the problem, and then that field forces the charge, that's the other part of the problem. So these two things are what we are going to majorly focus in this chapter, right? Coming back to the story